In this video, I'll explain what is homogeneous linear partial differential equations with constant coefficients and how to solve them. See the definition. If all the terms contain partial derivatives of the same order, then given partial differential equation is homogeneous. That means if there is a one term with partial derivative of second order, then the remaining all terms must be partial derivatives of order 2. There should not be a mixture of partial derivatives. If linear partial differential equation is the one in which powers and product of dependent variable and its partial derivatives must be absent. Suppose if z is the dependent variable and x and y are independent variables, then z into zx or z into zy or z into zxx, z into zxy, like that. Dependent variable and its partial derivatives should not be multiplied together, and every partial derivative must be of power 1. It can be of any order, but its degree must be equal to 1. Then we call such PDE as linear partial differential equation. Now, nth order homogeneous PDE in two independent variables x and y and a dependent variable z is given by, this is the standard form, where a0, a1, a2, a3, so on up to an are constants. That's why it is constant coefficients. These must be constants, and this is a function of x and y. In the case of ordinary differential equation, to say it as homogeneous ODE or not, we were looking at this term. If this term on the RHS is 0, it is homogeneous. If this term on the RHS is non-zero, then it is non-homogeneous. In the case of partial differential equations, we have to look at the partial derivatives of each term. If they are of same order, then the given equation is a homogeneous equation. Otherwise, it is not homogeneous. Here, this term may be 0, may not be 0, but that won't count while defining homogeneous linear partial differential equation. We have to look at order of each partial derivative. Now an example for second order homogeneous linear partial differential equation is this. The following notations I'll use throughout the video. Dou by dou x is represented as capital D, dou by dou y is represented as D dash, then dou z by dou x is written as P. This is partial derivative of z with respect to x, partial derivative of z with respect to y is Q. Second order partial derivative of z with respect to x is r. S is dou square z by dou x into dou y. T is dou square z by dou y square. Just to make our simplification easier, we are going with these notations. Now, how to solve nth order homogeneous linear partial differential equation? Let us see that. This is the standard form of nth order linear partial differential equation, which is homogeneous. So I am replacing dou by dou x in the form of d and dou by dou y in the form of d dash. Then you can write this entire expression as f of d comma d dash into z equal to f of x comma y. This is the standard form of a nth order homogeneous linear partial differential equations in terms of operators d and d dash. Now whenever you are solving nth order homogeneous linear partial differential equation, you have to first write it in this form, then its general solution is given by z equal to complementary function plus particular integral. So the complementary function is calculated based on different cases. I will explain that. Now here in this video, I will just consider those examples where f of x comma y is 0. So I will make one more video where f of x comma y is some other functions of x and y. So if f of x comma y equal to 0, in that case particular integral is always equal to 0. Therefore, the general solution is just the complementary function. Now let's see what is the working rule to find the complementary function. The first step is you have to always bring the given equation in the standard form, which is f of d comma d dash into z equal to f of x comma y. The second step is you have to replace d by m and d dash by 1 to obtain auxiliary equation. That is, you will get the auxiliary equation in the form a naught m power n plus a1 m power n minus 1 plus so on up to an equal to 0. Next, third step is you have to solve this above auxiliary equation for m. Then you will get different cases. First case is let m equal to m1, m2, so on up to mn. These are all distinct roots. There are no repetitions. In that case, complementary function is taken as f1 of y plus the first root m1x plus f2 of y plus m2x plus so on up to fn of y plus mnx, where these f1, f2, so on up to fn are arbitrary functions. Here the roots may be real or complex, but the roots must be distinct. In the case of complex roots also, the same method is to be followed. Second case is if k roots are equal, where k is either less than or equal to n. If there are n roots, out of n roots, because it is nth degree polynomial, there are k roots which are equal, other roots may not be equal. They are distinct. In that case, this is to be followed. But for those k roots, that is m1, m2, so on to mk, if they are equal to m, same, then complementary function is chosen like this. These are the first two important cases where distinct roots and repeated roots. Then along with that, there are four more cases. Those cases have to be remembered corresponding to a non-repeated factor d. If there is independent irreducible factor d, then complementary function is chosen as f1 of y. Corresponding to a repeated factor d to the power r, like d square, d cube, if it exists independently, then complementary function is chosen as f1 of y plus x into f2 of y plus x square into f3 of y plus so on up to x power r minus 1 into fr of y. That is same as this, where roots m1, m2 are equal to 0, because there is only one independent factor d. Now similarly, fifth case is corresponding to a non-repeated factor d dash, the complementary function is taken as f1 of x. That is, with respect to d dash, here the variable to be taken is x, whereas with respect to d, variable is taken as y. The sixth case is corresponding to a repeated factor d dash to the power r. The complementary function is taken as f1x plus y into f2x plus y square into f3x plus so on to y power r minus 1 into fr of x. I will explain this through some examples. Now see here, the first problem is, this is the given equation. The first step is you have to write down this equation into f of d comma d dash form. So d cube minus 7 into d dash square, because 1 with respect to x, second order derivative with respect to y, therefore d dash square plus 6 into d dash cube into z equal to 0. With respect to y, d dash, with respect to x, it is d. So now replace d by m and d dash by 1. There are no independent d and d dash factors, just it is a polynomial of d and d dash, and it is homogeneous because each term has partial derivative of order 3. Therefore, you have to find out the complementary function General solution contains only complementary function because right hand side is 0, no need to find out particular integral. Now replace d by m and d dash by 1. So you will get the auxiliary equation m cube minus 7m into 1, it is 7m, plus 6 into 1, that is 6, equal to 0. It is a cubic equation. You can go with the synthetic division method. 1 coefficient of m square is 0, minus 7, then constant is 6. We will check is 1 a root, write here 1, write this as it is 1, 1 ones are 1, 0 plus 1, 1, 1 ones 1, minus 7 plus 1, minus 6 into 1, minus 6, 6 minus 6, 0. Yes, 1 is a root. Therefore, m minus 1 is one factor. Then m square plus m minus 6 equal to 0. So, m equal to 1 is one root. Then other roots are given by factorizing this. That gives you m equal to minus 3 and 2. So, all the three roots are distinct. Hence, using that working procedure, complementary function is given by f1 of y plus x plus f2 of y minus 3x, second root, plus f3 of y plus 2x. Since f of x comma y equal to 0, the particular integral is 0. Solution of this equation is z equal to same as the complementary function, where f1, f2, f3 are arbitrary functions. Now the second problem is solve 25d square minus 40dd dash plus 16d dash square into z equal to 0. Already the given equation is f of d comma d dash into z equal to f of x comma y form. Moreover, every term has partial derivative of order 2, hence it is homogeneous. First, let us find out auxiliary equation. Replace d by m and d dash by 1. In this equation, we will get auxiliary equation 25m square minus 40m plus 16 equal to 0. So altogether this can be written as a minus b whole square, that is 5m minus 4 whole square equal to 0. M equal to 4 by 5. It is a quadratic equation, therefore two roots must be there. 4 by 5 repeated twice. Now it has repeated roots, hence general solution is f1 of y plus 4 by 5x plus x into f2 of y plus 4 by x. Then we can write it as f1 of 5y plus 4x plus x into f2 of 5y plus 4x. Now the third problem is solve d square plus a square d dash square into z equal to 0. So the first step here is write the given equation in f of d comma d dash into z equal to f of x comma y form. So replace here, already it is in that form. Therefore replace d by m and d dash by 1 in this equation. So you will get auxiliary equation as m square plus a square is equal to 0. Hence m square equal to, you will get minus a square, which implies m equal to plus or minus a into I. These are complex roots, but these are distinct roots. See here, if the roots are distinct, then complementary function is given by f1y plus m1x plus f2y plus m2x and so on. This is the method to write the complementary function. Here the roots are distinct, therefore though they are complex, we have to follow the same method. Z equal to f1 of y plus aix plus f2 of y minus ai into x. Now one more problem, solve d square d dash square into d plus d dash into z equal to 0. Now this corresponds to the cases from 3rd to 6th. The case here was corresponding to a non-repeated factor d, the complementary function is f1y. For a repeated factor d power r, the complementary function is this. Therefore, here First, these d and d dash are now existing independently as separate factors. And d is also repeated, d dash is also repeated. Therefore, you have to find out the solution corresponding to d square, then corresponding to d dash square. Don't go with the auxiliary equation method here, because it just gives you this part of the solution, and the solution corresponding to d dash, complementary function corresponding to d dash, will be lost if you go with auxiliary equation method, because we are replacing there d dash by 1, hence d dash gets vanished. Therefore, the solution corresponding to the factor d square is, because it is a repeated factor, f1 of y plus x into f2 of y. Same as this. f1 of y plus x into f2 of y. Next, the solution corresponding to the factor d dash, this factor square is, solution corresponding to the factor d dash square is f3 of x plus y into f4 of x. f1, f2 arbitrary functions used here. Take f3, but here it is x because it is with respect to d dash, and it is repeated factor with respect to d and d dash. Even if you write auxiliary equation for d, then its root is 0. That's why y plus mx term is not there, just y here. X, f3 of x plus y into f4 of x. Then the solution corresponding to the factor d plus d dash. Here you can write m plus 1 as the auxiliary equation. Therefore, root becomes minus 1. Hence, f5 of y minus x. Hence, altogether, this is the general solution.